Morning. Let's start with today's lectures. We have two lectures by Professor James Binney, but we've made a slight change to the program. He will speak first, then we'll have a lecture by Jacqueline van Gorkum, and then we have James Binney's second lecture. It's a slight change as we had it in the program. But here's Professor Binney with his third lecture.
Okay. Morning, everybody. So I want to talk about a good deal about the solution to this equation, because this is this Fokker-Planck orbit average Fokker-Planck equation that we derived yesterday, saying that the rate of change of the distribution function is minus the divergence of the flux through action space of stars is the equation that must describe secular evolution in pretty much every stellar dynamical context. And in order to make progress, of course, you need to know what these diffusion coefficients are. These things are going to vary through action space, and we need to know what they are. And I got as far as saying yesterday that they're non-zero because there are fluctuations in the gravitational potential coming from a variety of sources. And so what I'm now going to address is, so how do we calculate those diffusion coefficients, if you know what in terms of the potential, the gravitational potential of the fluctuations. So what we're going to do is take the gravitational potential and write it as a time-independent part. That's the part of our ideal model, idealized model, steady-state, etc. model, for which we've obtained the angle action coordinates, plus a fluctuating bit. So this is the time-dependent, chaotic, whatever. It's not necessarily chaotic. It's the time-dependent part of the potential, and it's created by what we're calling the fluctuations. And what we do now is slightly bizarre. We write this, which is a function of only 3 of the 6 phase-space coordinates, as a function of all 6 phase-space coordinates. So here is x0 just written down. For the moment, we don't need to worry about its arguments. And here is phi1 expanded as a Fourier series in the angle variables, because every function on phase space can be written as a function of the angles and the actions, and in terms of the angles, it will be a periodic function of the angles, because if you increase by 2 pi any angle, you come back to the same physical point in phase space. So we are always able to have this. Where's my arrow gone? Yes, we're always able to have this Fourier expansion, and here are some arbitrary phases that enable me to use this, to write this in terms of cosines only. So what we need to do is study, because what we're trying to do is calculate the diffusion coefficients. The first order diffusion coefficient is the expectation value of the change in time delta, the expectation value per unit time in the change in the action, and the second order diffusion coefficient is the variance of the changes in action. So what we want to know is, how does the action of our star vary as a result of having added in this fluctuational part of the potential? So we want to go to Hamilton's equations. So the rate of change of the action is the gradient of the Hamiltonian with respect to the angle variables. The Hamiltonian, of course, consists of the p squared over 2m, the momentum part, the kinetic energy part, plus the potential energy part. And when you take p squared over 2m plus this, you're getting the unperturbed Hamiltonian, which doesn't depend on the angle variables, so we have no derivative. So all we're left with when we take these derivatives is the derivative of phi1 with respect to the angle variables, which means the derivative of this with respect to the angle variables. And of course we can take that explicitly. That's not a problem, because we see explicitly what we've got. So here we have the equation of motion of the actions in terms of the angle action expansion of the fluctuating part. So now we want to integrate this equation of motion for a time which is long compared to the autocorrelation time, because we've got this picture that the actions are changing randomly by amounts delta. Well, of course, in fact, the action changes continuously. It's satisfying an equation of motion, but after some period of time, the action that you end up with is your original action plus an amount which is essentially random, because the fluctuations are random. So we need to integrate this equation of motion for some time, And the way we do this is a different kind of perturbation theory from the secular sort that I did yesterday. We say that the action at time t is equal to the unperturbed action, which of course is a constant, doesn't depend on time, plus a bit that you get by integrating along the unperturbed orbit, plus a bit that you get by integrating along the difference between the unperturbed orbit and the orbit you've attained so far, etc. So you do an expansion here essentially in powers of phi 1 of the fluctuations. We'll stop at this point. We won't go to this point. And similarly, you have that the angle variable is equal to the unperturbed part, which is the linear increase in angle over time using the characteristic frequencies, plus a first-order part that we'll get by integrating the derivative of theta along the unperturbed orbit. So this thing here is simply the integral of this equation of motion d time. That's all we need, actually. All right? And we can do that integral because into theta, we're working to first order. This is already a first order quantity because phi n is a first order animal. So in here, we can put in the 0th order value for theta, which is just the linear increase with time, and that brings us down to here. So this is our first order expression for the change in the action that the fluctuation will induce in time t. We want to obtain the second order diffusion coefficient. That's to say, I want to calculate the variance of the fluctuation in the action. So I multiply this equation for the change in delta, for the change in action by itself, and then I do a load of averaging. And the first average we do is over the initial phases, because I think I said yesterday that the change when we talked about how resonant islands scattered stars, that the change that an individual star experiences, whether it's trapped by the resonance or scattered over the resonance, is causal. It's not random at all, but it depends on its initial phase with which it encounters the fluctuation. So this theta 0 here is the initial phase of my star, and it varies from star to star. So our idea is that we're going to treat this, we're going to average over this because we want to know the statistical events, and we think that the stars in the galaxy are uniformly distributed with respect to this. So we're going to average, so we're going to take this commodity here, we're going to take this delta, multiply it by itself, so it will contain two integrals over time, integral dt primed, and then we're going to average it over theta 0. We do the integral over theta 0 over the phases. We do that first. We reorder the integrals until that's the first integral to do, and then we find ourselves doing integrals of this sort, right? This is the innermost integral. There's one of these signs coming from one of the deltas, and there's another kind coming from the other delta, which has a delta t, which has a t primed rather than a t. And we want to get the average value of this with respect to theta 0. Some simple trigonometry tells you that this average vanishes except when n equals n primed. And when n equals n primed, you can figure out what it is, and the answer is that it is this cosine. The integral becomes simply this cosine with respect to t, this cosine here. So now we've done the averaging over the angle variables and stuffed it back in here. We've got rid of one of the integrals, and we now still have an integral dt and dt primed. So next thing we do is we want to average over an ensemble of possible fluctuations. This thing here is a random variable, right? It describes the fluctuation. So this product of two random variables, one evaluated at time and one evaluated at time t primed, is a sort of autocorrelation of the fluctuations. And we're going to assume, it's totally reasonable to assume, that this autocorrelation depends only on the time lag. So if t primed is much later than t, we expect these two things to be uncorrelated, and therefore the average value of the product of these two fluctuating commodities will be 0. If t primed is equal to t, this is going to be the square of something, and so it will definitely be positive and non-zero. So the general assumption in situations like this in statistical physics is we say that because it's a stationary process, the random fluctuations will be the same tomorrow as they were yesterday, etc., that the expectation value of this product which is this overline means I'm going to take the ensemble average of this product, depends only on the difference of t minus t prime. So this symbol Cn is, by definition, this ensemble average of these two things, and the only thing we're putting in is the physical information that should depend only on the difference in time over here, not on the individual times. That's the stationary assumption. And of course, there's one for every n. N is a vector with integer components. This is the same over here. So we do that. We do this ensemble averaging, then we put this in here, and that winds us up here with this line here. And now we've got to do these integrals dt and dt primed. And to do these integrals, we make a change of coordinates. We're integrating over a sort of square. This is from 0 to a square in the tt prime plane, 0 to a big time. We're not saying exactly how big this time is, but it's going to be long compared to the autocorrelation of the field, the time it takes for the random fluctuations to decorrelate. We have to integrate over this square, and we do so using, obviously we want to use t minus t primed as one of the variables, and it's convenient to use t plus t primed as the other variable. So we make just a change of coordinates in the tt prime plane, and then because there's no mention of t plus t primed in this thing, we can do the u integration straight off. There's no function of u in here, it's just du, and of course v is appearing here and is appearing here, so is a material thing to do integral over. For this integral we get t minus mod v. And now the final approximation we make is we say, but after all, we said that t, big T, was going to be a time long compared to the autocorrelation time. What does that mean? Well, that means that this function here, which is a measure of the autocorrelation of the fluctuations, will be 0 whenever v is unless v is much smaller than big T, right? Because this is telling me how much correlation there is in time lagged v, and this is by hypothesis going to be 0 when v is on the order of t, and in fact it'll be 0 if we can make then t sufficiently big that we can basically neglect this term with respect to this. So we rub that out, and then this t simply comes outside the integral, and we find that the variance of the changes in the actions is now proportional to big T, which is the time over which we have waited. And the diffusion coefficient is definition the rate of increase of the variance with respect to the time. The idea in a diffusion process is that because you're adding things, because you're adding fluctuations in quadrature, you're adding the squares of little changes, right? It's a random walk process. You're adding the squares of little changes. The square increases linearly in time, and the diffusion coefficient in any diffusion process is the rate of increase with time of the square. So this big T, we hope is exactly what we want to find, is that this variance is linearly dependent on time. The coefficient of that is our diffusion coefficient, and so that enables us to write this very handy expression here. This says the diffusion coefficient that we want, which is the variance per unit time in the actions, I and j, is this stuff here, where C tilde is the Fourier transform of the autocorrelation function here. So C tilde is defined here. It's the Fourier transform. And so the Fourier transform of the autocorrelation is what's called the power spectrum, right? That's what it is. So this is a very simple and powerful result. It's telling us that the second order diffusion coefficient, with very few assumptions, is equal to the sum over these integers of the components of the integer, ni and nj are components of this vector here, times this autocorrelation, which is evaluated, notice, on the characteristic frequencies of the star, right? So when we studied these orbits, they were quasi-periodic. Their time series had line-like spectra, and the lines occurred precisely at these integer linear combinations of the fundamental frequencies. Omega naught is the vector of fundamental frequencies. So these are, in fact, the natural frequencies of the star. So what this formula is telling us is our ability of a star to diffuse through phase space is determined by the power in the fluctuation spectrum at its characteristic frequencies. A star has an infinite number of, in principle, infinite number of characteristic frequencies, though these characteristic frequencies are all linear combinations, integer linear combinations of its fundamental frequencies, and whether the star can diffuse or not depends on whether there's any power in the fluctuation spectrum at that particular value. Okay, so so in particular, suppose the fluctuation is periodic. For example, we'll study this in connection with spiral structure. If we had a totally steady spiral pattern or a totally steady bar or anything else that is periodic, then the power spectrum of the fluctuations will be line-like, and the only stars, which only a minority, an incredibly small minority of stars are going to be excited are going to pick up power, are going to be able to diffuse as a result of this, are those which happen to have one of their natural frequencies on the frequency associated with the periodic spiral pattern or whatever it was, bar. So, and in fact, this is a significant. So Selwood and Kahn back in '91 showed that if you start a disk with a gap in its angular momentum distribution, so there's an absence of stars at some particular value of the angular momentum LZ, this excites an almost periodic spiral pattern with a characteristic frequency that has co-rotation around there, and that this almost periodic spiral pattern that you excite then burns a hole. It does exactly this. It resonantly scatters stars out of its inner Lindblad resonance, so stars which have characteristic frequencies associated with its inner Lindblad resonance, and depopulates that region of phase space, which then becomes a region unpopulated and itself excites. It then becomes like the original gap. So you create another gap at a different place in the angular momentum distribution, which then excites another spiral pattern and so on and so forth, so that the disk, if you start off by creating one gap, it acquires gaps in other places as a result precisely of this tendency for stars to diffuse when there is something which has the fluctuations have a frequency with which they can resonate. So stars you want to think of as sort of resonators, antennae, which can pick up power at particular frequencies, and the consequence of picking up that power is they start to wander through action space. Okay, so let's talk about a little bit about observations. So the heating of the stellar neighborhood. So some combination of Hipparcos so Hipparcos measured proper motions, parallaxes, etc., for a load of stars within sort of good results for within 150 parsecs of the sun, and the Geneva-Copenhagen collaboration measured line-of-sight velocities for the F and G stars in that sample. And this diagram here from a paper I did with Alma, Michael Alma, was my thing gone? Yeah. Shows how, if you classify stars by color, so this is B minus V color, blue stars over here, red stars over here, you can group stars by color from the catalogs, and then you can calculate what their random velocity is. U is the random velocity towards the galactic, in and out in radius. V is the random velocity azimuthally, and W isn't on this picture, but anyway, it's so what you find is this very systematic increase in random motion with color. So redder stars have larger random velocities than blue stars, and the explanation for that is obviously that blue stars and the blue stars are relatively massive and therefore relatively short-lived. So if you're at this end, if you're at the blue end of the diagram, you're only seeing stars that have been around for some hundreds of millions of years, whereas if you're looking at the red end of the diagram, you're seeing stars that have been around or whole age of the, well, there are some stars in that group. You're seeing stars of every age. You're seeing ones made yesterday with low masses, and you're seeing ones that were made at the beginning of the galaxy because they have lifetimes that are longer than the age of the galaxy. So, and there's a preponderance of old stars here simply because star formation rate in the past was higher than it is now. So this diagram is giving us a direct indication of the tendency of stars to diffuse through phase space for whatever reason. It's because we can model this by considering stellar populations, allowing the stellar population considering. So you model this by saying there are a certain number of stars. There's a certain star formation history of star formation in the galaxy. The stars start with rather small random velocities, and then their random velocities increase like some power of time. And that then predicts what you have for this diagram. It predicts for what you have for how many stars of the different colors. You fit that to the data, and what you find is that the random velocity increases something like the third power of time. So Alma found that it went like t to the 0.35, which is within the errors the same as t to the 0.33. And it's interesting to ask, what can we say about the diffusion coefficients in the Fokker-Planck equation given this result? What dependence of the Fokker-Planck of these objects on action would yield that the velocity dispersion goes like the third power of time? So I'm going to do this under a reasonable but not wonderful assumption that the random velocity, so this number plotted here, is proportional to the square root of the average value of the action. So if I look at the stars that make this data point, they have a bunch of different actions, radial actions, but there is some average value for the stars in that bin, which is smaller than the average value for the stars in this bin, and there is some relationship between average value of action and velocity dispersion. If we were working in the epicycle approximation that I derived yesterday, then this would be an exact relationship. The random velocity would go like the square root of the average value of the action. So we're going to be using the epicycle approximation at that limit of accepting that that's a valid relationship. You can actually justify this kind of relationship more extensively than merely in the epicycle approximation, but let's not go into that. So the fluctuations, at the end, the other approximation we're going to make is that what accelerates these stars is fluctuations in the gravitational field generated by massive objects. So the prime candidates are giant molecular clouds, big clouds of gas that move through the disk with masses maybe of 10 to the 5 solar masses, scattering, and their gravitational fields scatter stars. Another possible, very rather likely source of fluctuations is the spiral structure. And a spiral arm is an object which might have 10 to the 7 or whatever. It might have, so it will have a very large, so the masses of the things that do the scattering are very large compared to the masses of an individual star. Now what that means is, so when a giant molecular cloud with 10 to the 5th solar masses encounters some M star, the M star suffers a significant change in its velocity. The question is, does the giant molecular cloud suffer a significant change in its velocity as a result of encountering the M star? The answer is clearly not. It makes negligible recoil. That's the key thing. That we're talking about scattering. If I consider the scattering of M stars by, shall we say, G stars in a star cluster, the G star does suffer a significant recoil as a result of scattering the M star. But in the case of scattering by molecular clouds, spiral arms, or whatever, the scatterer just simply doesn't notice that it's scattered somebody. So there's negligible recoil, and in those circumstances, we can. Where am I? Yes, keep going. I'm going forwards. That's the cause of the trouble. I want to go backwards. Sorry. In those circumstances, we had this relationship. So I said that when the scatterers, the diffusion coefficients, which are generated by a certain scattering process, have a temperature T, as in, for example, a star cluster, they definitely have a characteristic temperature T, then I produced an argument which said that this relationship between the first and second order diffusion coefficients has to apply. I now want to argue that because, and I can argue, if you want the details of this, you can find it in a paper by myself and Cedric Lacey in 1988, that in the limit of the recoil by the scatterers being unimportant, because they're so massive they don't notice that they're scattering the stars, that is effectively the same as saying that the scatterers have got infinite temperature, we use this relationship in the limit of infinite temperature when this term goes away, so the first order diffusion coefficient simply becomes the gradient of the second order diffusion coefficient. It's often a very good approximation. And why is this the limit of infinite temperature? Because you can imagine that if the M stars were left being shaken by the molecular clouds for an eternity, so that at what random velocity would they reach equilibrium with the molecular clouds? Well, only when equipartition had been achieved, when the kinetic energy, the random kinetic energy of a molecular cloud was the same as the random kinetic energy of an M star. So that the velocities of the M stars would have to be the square root of 10 to the 5 or more than the square root of 10 to the 5 times larger than the random velocities of the molecular clouds, which are on the order of 7 kilometers a second. So the point is that this point of thermal equilibrium is way, way away, is very, very far away. So that's why it's a good idea to put that T to infinity and adopt the very simple relationship that the first order diffusion coefficient is simply given by the gradient of the second. So this now makes our diffusion equation become a one that you now will rather recognize, I hope. That's this one down here. This is now looking extremely like the equation for diffusion in an ordinary gas, or the heat conduction equation in a plasma, because what we're saying now is that the flux of stars, this inside here, so this is of course a conservation equation. It says that the rate of change of F is minus the divergence of the flux. Now this is our expression for the flux of stars. The flux of stars in action space is now the second order diffusion coefficient times the gradient of the density. And that's exactly, in ordinary diffusion, it's the gradient in the density of whatever it is that's diffusing, which is driving the diffusion. The full Fokker-Planck equation is slightly more complicated because it includes what's effectively dynamical friction. It includes a tendency for everybody to slip back to lower energies. This is the point that Einstein understood when he did Brownian motion. He said he saw, you see Brownian motion, you see your pollen grains being jiggled around. So he said these pollen grains are exposed to a random kicks the whole time, and he grasped that if he didn't put in some friction on the pollen grains, they would pick up more and more and more and more and more kinetic energy and start to zoom around at ridiculous speeds. The fact that they sit there doing this forever, not picking up any speed, even though they're clearly exposed to random buffetings by random forces by the surrounding water molecules, that equilibrium is achieved between a frictional drag that they experience at the same time as they're being kicked around. It's a very general principle. It also goes under the name of the fluctuation dissipation theorem. Okay, so we've got a simplified form of the diffusion equation because our scatterers are so much more massive, and this is what we're going to work with. And I think it's a very good approximation. So the name of the game is to the ordinary diffusion equation has a Green's function where the width of it's a Gaussian, and the width of the Gaussian increases like the square root of time. I hope you've all seen that in your thermal physics courses. So we're going to do something that's analogous. We're going to say that we're looking for a solution where the distribution, the phase-space density of stars goes like t to the minus 2a times some function of the action divided by the 8th power of time. So this function, we're hoping this function is something definite and fixed, like a Gaussian, and then And then as time goes on, the typical width of the J distribution, of the action distribution, is going to grow like the 8th power of time. In order to conserve the total number of stars, we have to multiply by t to the minus 2a in front here. Oops. And the reason that I have a 2a there, not a 3a, is I'm making the following observation, that the stars are born on nearly circular orbits, so they're born on one of the axes of action space. So action space consists of its coordinate axes are orbital angular momentum, that's LZ, the radial action that controls how much motion there is in and out, and the vertical action that controls how much motion there is up and down. So these stars are born with negligible radial motion, this is the hypothesis we're making, and negligible in the plane, and therefore negligible vertical motion. So they're born on one axis of action space, and they're going to diffuse away from that axis towards larger values, non-zero values of the radial action, and non-zero values of the vertical action. So they're going to start oscillating vertically, they're going to start oscillating radially. That's the heating of the disk. So we're starting with a line-like distribution of stars, and we're watching fundamentally them diffuse away from a line. So it's going to be a kind of two-dimensional diffusion in the JZ plane, and I'm going to ignore diffusion in the LZ direction. I have to be a little bit careful about understanding what we mean by that, because in individual stars are most definitely going to diffuse in the LZ direction. But because there are always going to, because there are stars initially distributed all up and down the LZ axis, every time a star diffuses from big LZ to smaller LZ, some other star is going to diffuse from small LZ to big LZ, so that the net flux of stars along the LZ direction is going to be small compared to the flux of stars away from the LZ direction and the other two things. So we're going to focus just on the diffusion in the JR-JZ plane because of the initial conditions. And so what I need to ensure, I've lost it again, I want to ensure that the integral over J, this is over two directions, two dimensions of the JR and JZ directions in action space of F is a constant. So when I put in this hypothesis for F, then I need this t to the minus 2 alpha in order to make sure that as the width of the distribution grows, the amplitude grows proportional to t alpha. That's the width in 2 dimensions grows like t to the alpha. The absolute normalization falls like t to the 2 alpha, 1 over t to the 2 alpha. Okay. So now let's suppose the diffusion coefficients scale. So what I'm trying to find out is how these diffusion coefficients depend on the radial action. So I say let's consider the diffusion coefficient at k times the radial action. So I'm going to increase both JR and JZ by a factor k, and let's hypothesize that it scales as a power law. This is k to the b, and we're going to find out what b is, times the unscaled thing. If we now put in, because we're interested in calculating stuff as a function of x, which is j over t to the alpha, so let's put in, for one just thing, put in k is t to the minus alpha, and then we'll discover that the diffusion coefficient evaluated on x is t to the minus ab. That's k is t to the minus a, and then we're raising it to the bth power, so it's going to be t to the minus ab times j squared times the diffusion coefficient evaluated on j. Stuff all these hypotheses into the Fokker-Planck equation, and what do we have? We have this. After a bit of cleaning up, we have this. And we want this equation to hold at all times. So this is just precisely analogous to what you do when you derive the Green's function of the ordinary diffusion equation. Basically, what we want to do is get rid of all mention of time, so we're left with an equation that involves x only, right? And which will describe the shape of the function f naught. Well, the powers of time, here is the time dependence on this side, and there is the time dependence on that side. They have to agree, and they will agree if and only if b is 2 minus 1 over a. So the empirical result that the velocity dispersion, which is we're interpreting to be the square, velocity dispersion squared, which we're interpreting to be the expectation value of j, it goes like t to the 2/3, that's the square of t to the 3rd. That implies that a is 2/3, and that means that b is a half. That is to say that the that the second-order diffusion coefficient is growing like the square root of the action. This is what we have to understand. That's what the empirical result says. Now, in a famous paper, Roland Wieland, 1977, argued that what we're talking about here is a naive diffusion process, and that the data supports that the velocity dispersion increases like the square root of time. You can look at the formulae that we had on the last slide will immediately persuade you that if the velocity dispersion were to increase like the half power of time, like the square root of time rather than the third power of time, then that number b, which described how, that's that here, which described how the diffusion coefficient scales with action, then b would have to be 1. Now this is implausible. This can't be. And here is the physical argument as to why it can't be. In the epicycle approximation, the radial action, we derived this, is equal to the energy of radial motion divided by kappa, the velocity dispersion. Sorry, the epicycle frequency. So if I make a change delta sub r in j sub r, right, that's going to be proportional to the change in ER. The constant proportionality is going to be 1 over kappa. But the change through a scattering in the radial energy is going to be, because radial energy is a half v squared plus some effective potential, is going to be v dot delta v. That's the change in v squared, right? So what does that say? That says the expectation value of delta squared, which, if b is 1, is going to be proportional to JR. So this thing is going to scale with JR like JR. That's Wieland's hypothesis. It means that this change is the square of this, so it's going to be v squared delta v, but JR is going to scale like v squared, so we're going to have v squared delta v is proportional to v squared, so that means that delta v, the scattering in the velocity, is going to be independent of velocity. In other words, fast stars are going to change their velocity by just as much as slow stars are when they suffer a scattering event. That never happens. Why? Because the gravitational force is independent of velocity, and so the force depends only on the position of the scatterer and the thing that's scattered, and the time during which that scattering force works goes like 1 over v. Fast encounters at high velocity happen quickly, and the scattering force acts for a short time. So it's a generic property of Coulomb, or, well, in fact, gravitational scattering processes, that the change in velocity goes like v to the minus 1. It falls off with increasing speed. Fast objects are scattered by less than slow objects. So Wieland scaling isn't plausible, but you still see it very often reproduced because people think that, oh, this is a diffusion process. Diffusion processes lead to the velocity dispersion increasing like the square root of time. But the data don't support it, and it's totally physically implausible. Can we understand why? Can we, from physics, derive that the diffusion coefficient grows like the half power of radius? And I've just given an argument why the diffusion coefficient actually should be independent of radius if you follow this argument through, right? So, but the data seem to suggest that the diffusion coefficient grows like the half power of the action. Well, Cedric Lacey and I were able to show in '88 that if the classical Spitzer-Schwarzschild process does indeed give you the right scaling. So what this process is you imagine that your disk is perfectly tensional, and through this, so it's infinitely thin, and through this two-dimensional world, there wander these giant molecular clouds. And it was really a considerable achievement, I think, of Spitzer and Schwarzschild to do this in 1953, because in 1953 there was precisely no evidence for giant molecular clouds. This was a total figment, probably, of Lyman Spitzer's imagination, and it was kind of prescient, just as his invention of the galactic corona in the same time, maybe a couple of years later, was a total figment of his imagination until he built a satellite to detect it in the 1970s. So So you have this two-dimensional world, and through this cruise these giant molecular clouds, and stars moving fast on their epicycles, encounter these giant molecular clouds and are scattered by these giant molecular clouds. And you can work all that out pretty satisfactorily, pretty exactly, and you get the conclusion, the very satisfying conclusion, that process does in fact lead to this scaling of the diffusion coefficient. The trouble with the model is, the model unfortunately isn't really viable because the stars don't move in a plane along with the giant molecular clouds. They are, of course, oscillating in and out, up and down, and they oscillate up and down much further than the molecular clouds do. So as a star ages and heats up, it oscillates away from the molecular cloud layer more and more and more, and should be scattered by the molecular cloud layer less and less and less. So the diffusion coefficient shouldn't really grow by this process as rapidly as that. So I think it's a nice result in sort of theoretical astronomy, but I'm not sure that it unfortunately solves the problem. A conclusion that you come to, Lacey and I did, and also Lacey in his thesis had earlier, actually, with simpler arguments, concluded that this diffusion tensor, so that we've been calculating just one component, in fact, of the I've been talking about one component of the diffusion tensor. It's the expectation value of delta I, delta J, so it's a tensor. This diffusion tensor is very anisotropic. So, it's eigenvalues. It's a symmetric tensor, so it's characterizable by its eigenvalues, and its eigenvalues are quite different from each other. And the consequence of this is that we argued that the velocity in equilibrium, the velocity dispersion in the z direction would be 0.8 times the velocity dispersion in the radial direction. The stars would diffuse in such a way that they didn't have equality of these two velocity dispersions, but the z1 was 0.8 times the radial one. Observationally, the number is closer to 0.6 than 0.8, and we attributed this difference between 0.8 and 0.6 to the action of spiral structure, which was exciting only the radial motion and not exciting the vertical motion very much. And the molecular clouds it was their job to convert the radial motion to change the direction of the random motion and convert some of it into the vertical, and the disequilibrium that was being put on the system because the system was out of equilibrium because the spiral structure was driving in one dimension only, caused this difference in number. I think that conclusion is possibly wrong because, Jerry Selwood in 2008, in what's still only a conference proceeding, but that isn't because he doesn't believe it's true. Where has it gone? Jerry Selwood argued that we got our arguments are wrong because we assumed in working out certain integrals that the distribution of impact parameters, so the distribution of directions of closest approach between the molecular cloud and the scattering star, were isotropic, were in all directions equally, but actually of course we are more or less in a disk, and so there's a preponderance of impact parameters that lie roughly in the plane. There aren't that many impact parameters that lie perpendicular to the plane. And when in his numerical simulations, he did this by numerical simulation rather than by analytic arguments, but when in numerical simulations he controlled the amount of how far away the scatterers were, he could adjust this number and make it go from 0.6 when he didn't have any restriction on how far away the scatterers were to 0.8 when he had a restriction which meant that the only significant encounters occurred within a scale height. We're never further away than the scale height, so you might expect a reasonably isotropic distribution. So I think this stuff is probably more or less understood, although there are some loose ends one would ideally like to tidy up. How are we doing time-wise? So I've talked a good deal about. We've had a general framework for how the how the scattering works, and that we have some kind of diffusion. From the data, we know how the diffusion scales with action. I've talked a bit about specific calculations for how we would expect molecular clouds to drive diffusion. The other really important driver that you definitely can't neglect is spiral structure. And so I want to talk now about the way spiral structure works. So spiral structure is a very complex phenomenon. Obviously, many of its most important manifestations are to do with gas dynamics and not stellar dynamics, and so I deem those to be outside my field of overview. I'm not going to talk about the gas dynamics of spiral structure, not because it's unimportant, but because I understood my duty was to talk about stellar dynamics. And it is unfortunately difficult to get observational data on what is really happening to the stars in spiral structure. What is the amplitude, for example? What is the form of the spiral structure in the arms? Because the data are very heavily influenced by what's happening in the gas. At blue wavelengths, you're obviously heavily influenced by very young stars, which are formed in the shocks driven by spiral structure. Even at red wavelengths, which is the best place to be because you want to be sensitive to the old stars, the old low-mass stars are the way to go to ask, well, so what are the stars really doing? What is the gravitational potential generated by the mass-bearing stars doing? But even there, your photometry is influenced by giant branch and asymptotic giant branch stars. But Ritz and Zaritsky, here we go, and a few other people, I guess, about 15 years ago, did a bunch of work on near-infrared photometry of spirals, so that they studied spirals in at the wavelengths where there's going to be the largest contribution coming from lower mass stars, so telling you what the stars are doing. And here are some pictures from that study. And they inferred that a large part of what you're seeing here is actually coming from low-mass stars, which have order unity amplitude. There are inhomogeneities in the disk of the stellar disk of low-mass stars, which have amplitudes which are of order unity. So it's a serious phenomenon. It's not a linear, and crucially, it's not adequately studied in linear approximations. That's one reason why it's not a strictly linear phenomenon. What is absolutely clear is that the gravitational potential has an amplitude that's at least 7 kilometers a second. We see this in our own galaxy by looking at what's called the terminal velocity. So the largest radial velocity along a line of sight through the disk between L is 90 and L is 270, minus 90 to plus 90. So you see fluctuations in what naively you would interpret to be the speed at which gas is moving on circular orbits at different radii, which are on the order of 7 kilometers a second. You see similar fluctuations in the H alpha velocities of gas in other people's galaxies. So that gives you some sense of what the amplitude of the phenomenon is. Okay, so it can't be understood by linear theory alone. I think the current state of understanding is very unsatisfactory, partly for sociological reasons, I think, to do with how the subject has evolved in the last 30 years or so, the people who've been involved in it. I think it's a subject that I would encourage people to look at. But what's absolutely very clear is why galaxies, to me, very clear, why galaxies have spiral structure. They have spiral structure because it is the means, or a principal means, by which galaxies carry angular momentum from the inside outwards. And as we'll see in a minute, it's precisely through carrying angular momentum from the inside to the outside that galaxies can increase their entropy, and everything in the universe is trying to increase its entropy. That's sort of what it's all about when it comes down to it, increase its disorder. So that's the role of spiral structure, to carry angular momentum outward. Okay, so now let's imagine we've got an m-armed spiral structure. So there might be 2, it might be 4, it might be whatever number you like. So small number of arms, spiral structure. And let's suppose it has a definite pattern speed, omega p. So there is some pattern which is rotating at a steady rate, omega p. Then if you ask what is the frequency, if I stand in an inertial frame, remember we had this result that dE by dt, the rate of change of a star's energy, is equal to the partial derivative of the gravitational potential with respect to time. So ask yourself, what is the partial derivative of this gravitational potential as a function of time? The answer is it has a frequency which is m times omega p, because in a time 2 pi over omega p, m arms come by you. So this is the frequency, the fundamental frequency of this m-arm spiral. So therefore, if we ask ourselves, if we have a periodic spiral structure, we ask ourselves, what is the autocorrelation of the gravitational field? Right? We found that the diffusion coefficients depended upon the power spectrum of the fluctuating gravitational field. This fluctuating gravitational field is going to have a power spectrum which is a line at m omega p. So only stars which have a natural frequency equal to m omega p are going to be excited by this, are going to be allowed to diffuse as a result of this spiral structure. So a periodic spiral structure will drive diffusion, but only by a tiny fraction of stars, those stars which happen to have a frequency that coincides with this particular driving frequency. And in the epicycle approximation, the epicycle approximation is characterized by stars basically having the frequencies of stars depending only on position within the galaxy. In the real world, the frequencies of stars don't only depend on position, they also depend on the amplitude of the oscillations. Stars with small oscillations vertically have higher vertical frequencies than stars that at the same radius do large vertical oscillations. But in the epicycle approximation, the frequencies depend only on position, so if there's only stars with a particular frequencies are capable of experiencing diffusion in the epicycle approximation, these will be confined to a few rings. These are the important Lindblad resonance rings. So let's look at this diagram here. This is a plot. This is a Lindblad diagram. So along here is angular momentum around the symmetry axis. Up here is energy. This region here is inaccessible. There are no orbits in this region here because this is the curve. This curve along here tells you what the energy is of a star which has on a circular orbit with a given angular momentum. More angular momentum, more energy. More angular momentum, more energy. So, and stars on non-circular orbits have more energy than the minimum energy for that angular momentum. So eccentric orbits, so the circular orbit is the orbit with the least angular momentum for a given energy, or least energy for a given angular momentum. And as I go up here, I'm considering more and more and more eccentric orbits. Now, so what we want now to do is say, in this steadily rotating frame of reference, in the steadily rotating frame, if we move to that frame, the Hamiltonian, the expression for the energy will be a constant, and it will be this. The Hamiltonian in the rotating frame of reference is equal to the ordinary Boring energy of the star minus the pattern speed times the z component of angular momentum. This is a piece of basic classical mechanics. And in this rotating frame, the Hamiltonian has no explicit time dependence. If the frame that rotates with the pattern, the gravitational potential is constant. Everything is constant. So stars are going to move at constant h, constant Hamiltonian, and this Hamiltonian is conventionally called the Jacobi integral. So this is going to be fixed, and what's going to happen is that changes in angular, but the spiral pattern imposes torques on stars, so it changes their angular momentum. So any change in Lz is going to be associated with a change in E, so as to leave the Hamiltonian constant. So we're going to have a relationship, I can't see it here somewhere, but we're going to have a relationship which says that the change in the energy, dE, is equal to omega p, the pattern speed, times dLz. That means that stars in this diagram here are going to move along lines of a particular slope. The slope of the lines, so the spiral structure will cause stars to move like this at a particular slope. And here is a particular slope. This is a particular pattern speed. And where this pattern speed, where this circular speed curve, circular orbit curve, has the same slope as the pattern speed, that's what we call the co-rotation resonance. That is the radius at which a circulating, orbiting star moves around, riding round with the pattern speed. So stars are going to move up and down this line. Now, but wherever we are, oops, I've lost it again. Wherever we are, here they'll also move parallel to this line. Down here, they'll move parallel to this line. So consider a star down here at the inner Lindblad resonance. So this star has a frequency which can resonate with omega p. We'll talk about that in a moment. It must move along this line here. It can't move up here because there are no orbits up here to move down to. So therefore it moves down. Up here, there's a star that also has a resonant frequency, is able to resonate with the spiral. So it's capable of changing its angular momentum, it's capable of diffusing, but it has to move parallel to this dotted line again. It can't move down because that would carry it into the unphysical region where there are no orbits, so it has to move up. So the key thing is that these stars at small radius lose angular momentum. They move this way. These stars with a large radius gain angular momentum and move this way. This is the inescapable conclusion for this line of argumentation. And stars at both at small radius at the inner Lindblad resonance and at large radius at outer Lindblad resonance, the stars move from being on circular orbits on this bounding curve to being away from the bounding curve, which means that they move to more eccentric orbits. They move from circular orbits to eccentric orbits. So the disk is going to be spiral structure will heat the disk, especially at the inner Lindblad resonance down here because of the curvature, to a lesser extent at outer Lindblad resonance there. And at co-rotation, stars will be able to move either way. Some will move to larger angular momentum, some will move to smaller angular momentum, and they will move from circular orbit to circular orbit. Yeah. So it's in that sense, I mean, that's a demonstration that spiral structure moves angular momentum outwards, essentially from inner Lindblad resonance to outer Lindblad resonance. Okay, so at co-rotation, you have this idea that stars can move either way, and in fact, stars will be moving either way, and the way I like to think about this is stars swap orbits, and we're going to just talk a bit about that. So Jerry Selwood and I investigated this phenomenon in 2002 with n-body disks in which Jerry seeded a groove, so he used this mechanism that I mentioned earlier of that Selwood and Kahn discovered, that if you arrange that there's an absence of stars at some particular angular momentum, you excite a weak spiral instability which has co-rotation at that radius. So he did that so as to have a sort of controlled experiment. And this spiral feature grew and then it fades away, and because you're inside an n-body experiment, you can see what's going on. There we go. So this is a plot of the change in the angular momentum of stars versus the angular momentum of stars. This line here is the co-rotation radius. It's the angular momentum associated with co-rotation of the spiral pattern that Jerry excited in his disk, which we're able to measure and therefore know what its pattern speed is. This is the radius of the inner Lindblad resonance that you calculate from that. This is the radius of the outer Lindblad resonance. Sorry, I should have said about what the Lindblad resonances were. They were on the previous thing. So the resonances, we know, always occur when the natural frequencies, so an integer an integer combination of the fundamental frequencies is equal to the frequency of the imposed whatever it is that's shaking the gravitational field, right? And the co-rotation is the case where this vector here consists of nothing in the radial direction, m in the LZ direction, nothing in the vertical direction. So we simply have that m omega naught is m omega p. M times the going around and around frequency is equal to m times, that's just expressing co-rotation. The inner Lindblad resonance is where the first component of this vector is -1, the second component is m, and the third is nothing. So we have that in the epicycle approximate, we have minus omega r plus m omega going phi, going around and around, is equal to m omega p. So we have that omega r is equal to m omega phi minus m omega p. What that's saying is that the frequency at which the star experiences the spiral structure, which is m times the difference between its frequency, its going around and around frequency, and the rate at which the pattern is going around and around, so that's m times omega phi minus omega p, is equal to the radial frequency. So that frequency which it experiences is the frequency which it naturally oscillates this way. And the outer Lindblad resonance is merely differs in the change of sign here. So at the outer Lindblad resonance, the pattern speed is bigger than the going around, than the circular frequency, the going around and around frequency. So you want to say that m times omega p minus omega phi is equal to omega r. So that's these most important low order resonances. Okay, so what you see here, so this, of course, individual stars have changes in this n-body disk. Different individual stars have different changes in their LZ. So here we have at a given LZ, you consider all the stars that have the same LZ, you have some distribution of changes in LZ as a result of this excitation. And this is showing the 20th and 80th. This is showing the width of the distribution. This is showing the center of the distribution. So the thing, however, is that if you consider stars that are in the neighborhood of co-rotation with the resonance, these stars which have less angular momentum than the circular angular, than the resonant angular momentum, than the co-rotation angular momentum, gain. They have positive delta L. And these stars, which are outside, have negative delta L. So these stars gain angular momentum and move out here. These stars lose angular momentum and move in here. This is the swapping process. How does this look like in the real world? This is a disk. So each of these lines is an orbit of a star. This is radius. In some toy model, right? This is the co-rotation radius. This is 1.5 times it. This is half of the co-rotation radius. And this is phi, the angle going around and around from pi over here to minus pi over there. And so this is sort of a disk unwrapped from being circular to being looking like this. On this, we've imposed a growing spiral pattern, and this is showing what the orbits in this spiral pattern look like in this toy model. So the stars on the outside are moving like this, and the stars on the inside are moving like this. And you can see the stars on the outside are all set rippling by the spiral pattern, and stars at co-rotation are suffering this entrapment I discussed yesterday, all right? So actually on co-rotation, at one phase, this star just rides with the spiral pattern. Stars with slightly different initial phases orbit around it. Right, so we've got these trapped orbits, and then we've got here. So these are trapped orbits, librating. These are circulating. So what happens here is that as the spiral in the n-body model, as the spiral structure grows, these resonant islands appear and grow. And so in the unperturbed disk, we just have stars moving horizontally at all distances from the center. As the spiral pattern is switched on, this resonant island grows, and stars which had less angular momentum than the resonant angular momentum, the co-rotating angular momentum, which were down here, some of them get swept up into this growing island, and then they move for a while around this resonant island from inside to outside, and then the spiral structure fades away, the island shrinks, and they are released on the other side of the island. Meanwhile, stars which were picked up on the outside of the island, which had more angular momentum than the co-rotating angular momentum, ride around on these trapped orbits and are released on the inside. So that's the swapping process. And this is the dominant effect, it turns out, of spiral structure. So in another experiment, we set up... we just set up a disk that should have been stable and so on and so forth, and integrated it for about 5 gigayears. And very weak spiral structure emerged. You could see very, very weak spiral structure emerging as the disk, as the thing evolved. And then it's possible at the end of the experiment to ask, so where is the radius at what radius do we now find stars? What is the guiding center radius? So what's the radius associated with the angular momentum of the stars which, for example, were originally had guiding center radii here? Well, the answer is it's this kind of broad distribution. So this is telling you this is a histogram of the final guiding center radii of the stars that initially had this guiding center radius. In the main body of the disk, you can think of this as in kiloparsecs, although it's in toy variables. In the main body of the disk, you see you have a width which is 1.5 or so kiloparsecs wide. We have sort of vaguely Gaussian distributions where we have distributions of a certain width, and that characteristic width is on the order of 1.5 kiloparsecs wide. And this is a disk which had very weak spiral structure, weaker than Ritz and Zaritsky saw in real disks, and was only integrated for about 5 gigayears, not for a whole Hubble time. So this orbit swapping is a very effective process, and it's scrambling the radii of stars without heating them. The crucial thing is that the stars are moving from almost circular orbit to almost circular orbit. They're not increasing their random velocities very much by this scrambling process here. I think this is probably a good moment to stop, because this is slightly this is the next development of the same topic. So why not, since I think time is drawing to a close, why don't I stop now and take any questions that anybody has? Yeah, so questions?
If you added a bar into this situation along with spiral waves, what effect would that have on the overall diffusion?
Well, profound, because so a bar is obviously a very strong perturbation in the region of co-rotation, and I think we saw a little of this yesterday. We'll certainly, I'm sure, see more of it today in Leah Rathanasula's talk, that resonant, there are we saw, what Leah showed us yesterday was a series of resonances which arise as you approach co-rotation. We saw triangular sort of orbits, and we saw rectangular sort of orbits, and orbits with extra wiggles, extra loops on them, right? So there's this series of resonances. And remember what I said yesterday about when you have a load of different resonances which are all fighting for possession of, all seeking to entrap neighboring orbits, you end up with a sort of a chaotic walk through phase space. So I think that's this sort of, here what we're seeing is a nice orderly, there's basically one resonance in play, and there's a nice orderly movement around it. So we are getting a mixing, there's a randomization going on here. We are getting a mixing of the disk, which has important implications for chemical evolution, but we're not getting a general outbreak of disorder. In the case of a bar, the extra strength and leads of the rotating gravitational potential leads to a fight breaking out between the various resonant islands, which leads to chaotic diffusion. And this isn't properly, I think it's, to my mind, the correct description and understanding of what this does to galaxies isn't in place. So I think that's kind of a frontier of the subject.
Hi. I was wondering about the halo star. Are they important in order to calculate the diffusion of...
the halo stars?
Yes.
No, I think when we're discussing the diffusion of the disk stars, they're unimportant because the fluctuations that a halo star would produce acting independently of one another, right, is just two-body scattering. And as I explained yesterday, two-body scattering is unimportant in galaxies. Now, what potentially is important is that the halo stars do not act independently; they act cooperatively, right? So we know from Bell et al. Or whatever, we know from the SDSS work that our halo is, that I think Bell et al. 2007, 2008, I'm not sure, say that at least 50% of the stellar halo is comprised of streams, lumps, and these things are not properly understood. I mean, so we all know that there are beautiful streams in there, but there are also strange features which nobody has any proper explanation for. I think it's mysterious why it's as lumpy and bumpy as it is. So those things are potential scatterers. Now, I suspect that they are still not important because the total mass of the stellar halo is extremely small, so that even if we have a lump which contains, shall we say, 10% of the stellar halo, I don't think it would be a significant scatterer. What we have to ask ourselves is what is the effect of there presumably are associated dark matter lumps. So most of the halo, most of the mass of the galaxy is invested in the dark halo, and a significant part of that will be invested in the same phase-space region as the stellar halo, and the lumpiness of that is what we really have to be concerned with. And again, I don't think we know the answer to this, how important the fluctuations are which are generated by that. But I do think they're important. Why do I think they're important? Partly because of the sort of phenomena that Jacqueline Van Gorcon showed us yesterday of lopsidedness and especially warps. I'm completely convinced that warps have to be transient structures generated by lumps, by streaming lumps, non-equilibrium phenomena in the dark matter halo. And they are launching waves into the disk, and those waves will heat the disk in much the way that I've described, right? And they should be described by these diffusion coefficients, right? So one of the things that we need to do is to understand what diffusion coefficients those sorts of phenomena drive. Hasn't been done. Yep. There's a question over here somewhere.
I was just wondering, how does the diffusion change along the spiral?
Well, along the spiral, to some extent, this diffusion. I mean, so I want to understand this. I want to see this as happening in action space, right? So it's not in real space. It's in. So because stars move, because a star moves in the course of its orbit, right, radially over a couple of kiloparsecs or something like that, and it moves somewhat vertically, it's a rather delocalized thing, and it's sensing what happens. So diffusion isn't happening at a point in the spiral arm. The spiral arm is affecting all the stars in different ways. The dependence of the diffusion coefficient on the action is measuring how, and as I say, stars are rather, by the time they're on eccentric orbits, they're rather delocalized things. So I don't want to think about it as happening terribly. I'm a little bit willing to think of it happening at a particular radius, but I'm very unwilling to think of it happening at a particular azimuth.
There is a way to minimize this diffusion?
To minimize it?
Yes.
Why would we want to do that?
I know, if you want to have it in place with stars, do you want to move?
If, for example, in an n-body simulation or something, well, what you've got to do is keep the noise down, right? And it's very hard to keep the noise down. I mean, it's one of the things I need to discuss in the next lecture, that disks are very responsive systems, and they amplify whatever noise there is. Moreover, noise in them feeds on itself. I talked about that slightly in the context of Jerry Selwood, the Selwood and Kahn groove process. So I think the bottom line is that it's impossible to eliminate this noise. So one of the things in his retirement that Alaa Toumari does, I mean, if you go and visit MIT, he always has a new, even better simulation of a disk which is completely stable by every known stratagem, right? And then his computer has been integrating this for the last several months, and it starts off with some incredibly small little bits of something or other. You can't really see it, and it grows and it grows and it grows. He says, "Why is this happening?" So disks are they are just determined to pick up if there's any little stimulus. So you start with a disk which is formally stable. It will pick up from somewhere, from the Poisson statistics you started it with, but then there are people who work, like Jerry Selwood, to suppress that. But you just simply cannot hold them back. Eventually, they start to shake, and then they shake more and more and more, and then they burst out into some beautiful bar. They're irrepressible. Is that fair, Leah? There's a question here, I think. Oh, there's something over there.
Yeah. About the amplitude of the spiral arms in mass. These papers by Rix and Zawitsky and so on, they measure K-band.
Yeah.
And as I showed, well, it was last week before you were there.
Before I was here, right.
In K-band, what you basically see is AGB stars and red giants. So basically no dwarfs. But on the other hand, so you see through the dust and the giants, when there are giants, there are probably also dwarfs. And somehow if the K-band is less sensitive to young populations, so it's indeed the best way probably to convert light to mass. Still, where the problem of where the mass really sits is not well solved. If you assume, for example, that there's lots of giants sitting on top of...
So you don't accept their estimates of the contribution, the significant but not dominant contribution of the giants?
No, I think this is still something that has to be looked into.
Right. So presumably it's possible to do some kind of tonnery analysis of the fluctuations in order to take out the contribution from the... Isn't it?
It's a mess. That would not work. That's too difficult for that.
It's too difficult. Okay. Right. Well, you're the expert, so I defer to you.
Excuse me, James.
No, we have a question here, I think. They're next, yeah, okay.
There is some work that is done in the Academy of Athens by Voglis and Tsoutis some years ago. They support that spirals arms in barred galaxies are supported by chaotic orbits emanating from Helena and L2 stable points. I mean, is there any connection between this?
I don't have any problem with that being the case, and I think probably Leah's going to talk about that. Yeah.
Problem.
But the point is there are still fluctuations. I mean, there still is going to be associated with fluctuations, non-axis symmetries in the gravitational potential, and then we need to ask ourselves what are the time characteristics, what are the temporal evolution of these fluctuations, and depending on the answer, we'll be getting some level of diffusion. So then please.
Got another one for you. If spiral disks are, this incredibly active sort of dynamical environment, Is there any hope for understanding their formation based on stellar population gradients?
I think there is modest hope. That is to say, I think the modeling of the chemical and so what is absolutely clear is that you have to model the chemical evolution in parallel with the dynamic evolution, right? We've known this. This is obvious. We've known this since the 1950s. Well, I was only at the time, but it was one of the discoveries of the one of the important results of the early 1950s by Nancy Roman and people, that there is this intertwining of chemistry and dynamics. And there's been far too much work modeling the chemical evolution of disks under the assumption that you can divide the disk into a series of annuli and stuff. And I think this should have stopped a long time ago. I think it is now stopping, but so this has to be done. And I think I'm trying to describe what I think is the correct framework for doing this. So Ralf Schönrich and I had a go at doing this a couple of years ago, and I think that sort of work is showing its age. I would like to move on from it because it is something you really want to do with this diffusion in action space. You have to. So the name of the game is you're creating stars along one axis of action space, right? As I've described, the nearly circular orbit axis, and then you have an interstellar medium which is also distributed along this axis in action space, with a chemistry which is a function of position and time. So it's at each position it's evolving, and we need to keep track on that. That's the chemical evolution part. And then simultaneously the stars are diffusing away from there depending on whatever the noise is in the disk. So I think the relatively easy part of the problem is the chemical evolution part, because people have worked on that for a long time. And the part that is still very unsatisfactory is the diffusion through action space away from there. The trouble, of course, so you say, will we be able to understand the evolution of galaxies by studying this stuff? This is the best that you can do, and the outlook is moderate but not wonderful, because fundamentally you're dealing with a diffusion process, and all diffusion processes are processes by which nature erases its trait. I mean, which you lose information, right? And the reason nature is erasing its footsteps, its track of how it has arrived at this particular point. So, I think only by working at this kind of modeling will we understand to what extent we are able to make inferences about the past. And I certainly don't buy. I mean, so there are papers by Sales et al. Or whatever, talking about, the eccentricity distribution, this is the flavor of the year. You look at the eccentricity distribution of stars in the Rave catalogue or somewhere, and then you draw some inferences about whether the thick disk formed by infalling stuff or fattening stuff or something else. This I don't buy at all. I think this is just absurdly naive. We have a lot of work to do in order to make any progress with this. How much progress we ultimately can make, we will only discover by doing the work. It will be moderate. We are not going to be able to say exactly this is what happened, because it is a diffusive process. It erases information. Other questions? Coffee time?
Okay, thank you to the speaker again.